what you can expect from the talk today. What will we talk about here? This talk will be divided into 3 sections. The first section will be what does the compiler and the CPU does to your program. Will it optimize it? Yes. Will it make it different? Maybe. The second part will be the hardest part, in my opinion, and we will talk about memory ordering and memory fences. We will get into all the types, how they work, what is the difference between them, and how to make it work correctly. Because there are interesting edge cases there that we should talk about and discover and understand how to use them correctly. And the last part will be the practical part. I will show you how those things are implemented with C++11 to C++23. I will show the new tools that we got with threading, and basically you will have some tools after this talk, hopefully. I have 175 slides to go over. Today at 3 a.m. I removed 35 slides, and that's why we have only 175. I hope we will squeeze everything in, so let's begin. Okay, few words about me. I'm Alex. I have more than 70 years working with C++. Usually I work with large systems. And right now I work in a startup called Speed Data. Speed Data is basically the next big thing in big data. We will help you accelerate your queries. We are creating a new CPU, general purpose CPU, that doesn't work with von Neumann. We will get to von Neumann soon enough. And basically, it's going to be amazing. We have, our CPU is coming really soon, and stay tuned to that. I post in LinkedIn once a week, usually thoughts about C++. I try to teach new features, and sometimes I ask crazy riddles. So for people that don't like riddles, still go and see me. And I started the site. So if you want to see all the talks I've been through, you can go to the site and you can see all my talks in one place. And you can see I'm starting a new blog post. And I think I will start streaming videos as well that explain the code that I'm writing. Okay. So let's start our talk today. A first and very important question is, does the processor execute your code exactly as you wrote it? Who think it does? Wonderful. So the answer is usually not. The longer version of that answer is, compilers may reorder your program. They may change operation. They may do things differently than you thought you were writing. And then CPU can reorder more things, and it can use out-of-order execution. And everything is basically out of order, and it's not exactly how you wrote it. Let's start with compiler optimizations. What the compiler does for us. And to start that, I want us to play a role of a very, very simplistic compiler. So we have a simple code snippet here that sets n to be 100, and it is a const expression. We have a function that creates a data array of 100 values, and those values will be iota values, deterministic function. We have a psum. We have a loop that loops from 0 to 99. We have a deterministic function that's called pivot that receives n, and it will always get us the same number. It's deterministic. Afterwards, after we will have p and we have I, we're accessing our data in I and p, multiplying it and summing it into psum. So let's play the role of the compiler. What would you do with this code? And again, be simplistic. Yes?
Internal compiler error.
Why?
Because I'm not a compiler.
Okay. But it's a game. Let's try to play. What would you do? Yeah, Chris.
If the inputs are fully defined and everything is completely deterministic, it could just compute the result.
I said simplistic compiler. Yes.
Pull pivot out of the loop.
Pull P out of the loop. Great. Why?
Because it's a constant, it's a function of a constant for the loop. So extract it out of the loop and don't recompute it on every iteration.
And that's because calling a function all the time is something that's very pricey. And maybe this function does a lot of things inside it. So yeah, that's great. What else?
What does get int array do?
Get int array, think about it, it's something that returns a series of numbers from 0 to n that it's provided.
So it can optimize away the function, right?
Maybe, but again, a simplistic compiler will not do that.
Well, I can tell you,
Yeah,
if you want to know.
I really want to know, please.
You're going to take the P out because it's fixed. And that
Yeah.
means the data P is also fixed.
Yeah,
So while you're indexing into it.
great. So we'll take out data P as well. And what else? One more thing that the simplistic compiler may do here.
Instead of multiplying each time, sum up all values and do one multiplication at the end?
Great, thank you. So that's the three simple things that we can start with, and that's exactly what I want us to get to. With those three things, we already did something to our program that will not run the same way that you wrote it, but it will run better. Your performance will get better because the compiler thinks and knows that it will get better.
A pretty poor coder who wrote that code.
Thank you. It's supposed to be poor. Okay. Now let's talk about compilers that are modern and have more things in them, and they're not simplistic anymore. So we will start, if you have x86 machine, it has vectorization operations. Basically, in this case, the compiler thought, I have a series of numbers. As you can see, this is a series of numbers. I can split them up into quad words and then use vectorization mechanism here. XMM registers are considered to be vectorized. So it does everything on chunks of four words, and it will make our program much, much faster. Chris, this is not a simplistic compiler. So if everything is known during compile time, we can just calculate it during compile time, and the program will just return the number, and that's it. Your compiler knows math. So it will always try to simplify your algebraic equations. For example, if someone, a very bad coder, will write this code, variable plus 1 plus 3, the compiler will say, okay, it's the same as v plus 1 plus 3, and that's the same as v plus 4. So instead of doing a couple of assembly operations, we will do only one operation instead. Furthermore, it does more for us. So it knows and understands how your CPU works, and it knows which operations are pricier and have more latency, and which operations are easier to execute and will give us better throughput. In this example, we have a code that does add and divide with unsigned integers of 64-bit. It adds 1 plus b, which is a very simple ALU operation, but then it divides by 2. Dividing is the most horrible thing that you can do in your code. The latency for division is the most horrible thing. It's very, very slow. So here, the compiler is smart enough to do a couple of things. It will use LEA, which is a weird name because it's not doing exactly what it means. It means load effective address. It's not loading any effective address here. It's just a neat trick to sum a couple of numbers instead of creating a couple of assembly operations. So here we don't need to zero RAX. We can just do it in one operation. We are moving RDI plus RSI to RAX, and then we're removing complexity. We are removing the straight of the operation. The compiler can see it. Dividing by 2 is the same as shifting right by 1. Shifting right by 1 is an ALU operation. ALU operation is the easiest operation that your CPU can run. So instead of running a code that is very complex, we are running something that is really simple. And with my shameless self-promotion here, if you want to know more about things that the compiler does with sign and unsigned operation and how to use them correctly, you can watch my talk from Core C++ 2023, where I explain in details what the compiler and how we shouldn't write code. Okay, more things that the compiler may do for us. Branching is an expensive operation as well. When you branch, your compiler or your CPU needs to understand that the branch will be taken or not taken. It uses some complex operation like branch predictions, and this may stall your pipes. We will get to there soon. But it's preferred not to do branching. And if your compiler can see into your code and think that you can do something sequentially instead of branching all the time, it may open up your loops or remove them altogether. So in this very simple code snippet, we're looping 5 times and printing hello world. The compiler is smart enough to understand I don't need branching at all. Everything is just rolled out, and we are running one basic block sequentially. It will be much faster than do it in a loop. The compiler will remove that code for you as well. So if a very, very bad programmer will write something like that, where you have 2 integers, you have a loop where you increase I and you increase j in the same time, but then j is not used at all, the compiler will see through your code. It will understand that j is not used. It will poison it. And then it will understand even more. You don't need the loop. Why do you need this loop? You know exactly the size that you want I to be. So just return I. And that's exactly what the compiler does. XOR AX and AX is just a fancy way of zeroing out AX. Test is to see if the parameter that we got is not 0. CMoveG is, it will move only if the flags of the test are 1 and not 0. And then we're returning AX. That's it. Yes?
Is the result is out of optimization option, like level 2?
That's level 2, yes.
Or 2, right?
Level 0 will not do that. I think this even can be done in level 1 because it's really simple for it. The vectorization is level 2. The removing all the code altogether is between level 2 and level 3, it depends. Yes?
So this assembly will return 0 if size was negative. And the compiler can do anything it wants, right? Because it's undefined behavior.
It's an integer, so yeah, it's not an undefined behavior if you think about it. It will just loop all over it.
So if
You have just integers here, so no undefined behavior.
then this loop,
Yeah. It will just loop for a large number. If size is something that is like very large, and you are just saying that I is smaller than size, yeah, it will never, yeah.
it should return 0.
Always return 0.
Okay, inlining a function. So, as I mentioned before, calling a function is a costly operation. We don't want to do it all the time. And if the function is simple enough, and each compiler has a different way to look at those things, it may inline your code. In this example, it's a very simple example where you're taking the integer that you're receiving to a function and adding 1 to it. Then inside main, you are using add 1 with C. the number of parameters that you got. So in this simple operation, the compiler removed everything. It inlined your code. I specifically wanted to use C because it cannot optimize it out. So it removed your code. It's taking C and adding 1 to it, and that's it. You don't call a function. You don't do anything. And it goes even further. Who knows what a tail recursion is? Few people, so I will explain what a tail recursion is. Tail recursion is something that is broadly used in functional programming, Peter. And, and it's a very nice operation because it's using recursion to create a loop. Basically what it says is we don't have to backtrack what we are doing in this recursion. The compiler sees into it easily and understands that because I don't have to do it, I can inline it. I can calculate it, and I can understand it. In this simple function, it's even better because all we are doing here is a fancy way to add things. Never write this code. But it's just adding A to N. That's it. That's all it's doing. Inside main, afterwards, it's using C and C plus 10. So the assembly that we will get, let's look at the function. No recursion here. It's just one assembly operation. We could optimize out everything, and we remove the loop itself because we are just adding RDI to RSI. That's it, as simple as that. Inside main, we can also see what it does to algebraic calculations. So it's so that it uses C and C. C and C is twice C. So it multiplies RDI by 2 and adds 10. That's it. Because the code is on 86, multiplication is an easy thing to do. If we were on a different architecture, it would be problematic and it will not output this code. It will just say RDI plus RDI plus 10. Okay, that's it about compiler optimizations. Any questions that anyone wants to ask? Great. Now let's talk about what your CPU does for you. It's gonna be a taste of what the CPU does, but we need to understand what it can do for you. Before we start, we all need to understand that there was a mathematician in 1940s. His name was von Neumann, and he invented the modern CPU. A very simplistic model that says that we have inputs and outputs, we have registers, we have logic units that do things, we have a control unit, and an external memory to our processor that can be used to store data and get data. Until today, this is the model that runs in most of your processors. Not exactly the same. We added a lot of things, but the basic principles are the same here. And if you want to know more about computer architectures and CPUs and how it's used, and then see how a lot of fancy templates that I write, you can go to my talk from 2022 about high-speed query acceleration. Now, most of the CPUs used to use INO. It's in-order execution. In-order execution, it means that everything is done sequentially. But that's not good enough. Why it's not good enough? Because some operation may take more time than others, and we want to pipeline those things. We want to pipeline those things because we want a throughput of one instruction in a cycle. And that's why the pipeline was invented. This is a very simplistic pipeline that has only 4 stages. The first stage is fetch. Fetch is taking the instruction from the instruction memory. Then you have decode. Decode is decoding this instruction and understands which registers or which memory units it should use. Execution is sending it into a FPU or ALU. And then we are writing it back into a register or into a memory. And if all the stars are aligned correctly, we will have one instruction in a cycle. Alas, things don't work as we want them. Some instructions take more, and because everything must be sequential, If an instruction goes into memory, it takes many, many cycles to calculate. It will stall all the other instruction until it's done. And that's exactly why out-of-order execution was invented. Out-of-order execution says, if I don't have relations with other instructions, I can execute everything without stalling. And this is a very simple and great example for that. We have a write to the memory, and we have addition of R4 and R5, and we have a subtraction of R6 and R7. None of those instructions have relations to each other. There is no reason to stall here. But because we are in order execution, we must stall until the execution operation is done. The same thing in out-of-order execution will be executed all together. And then we will just need to wait for the move operation to finish, and we will commit all the other operation at once. This is a basic diagram of how out-of-order CPUs look. We have fetch, as before. Still, we have to have some in-order execution here. We have a branch prediction. I will not go a lot into it, but it's a very important unit in your CPUs that predicts basically if a branch will be taken or not, and that just utilize our pipeline even better. We have the decode operation. We have then, after the instruction is decoded, it moves to the issue queue. The issue queue waits for the functional unit to be open. If we have a functional unit and we don't have hazards, we go, we write it in, we execute it, we write it back to the reorder buffer, and then we commit it. We commit it after all previous executions are done. And it is done by dynamic scheduling. First, we fetch the instruction, as I mentioned. We dispatch the instruction into a queue. If all operands that are worked with this instruction are already available, we can move it to the functional unit. And after we move it to a functional unit, it's go to the reservation station. And if all other operations are already done and can be committed, we can commit it. But it saves us a lot of time. To do so, we need to check for a couple of hazards. We have the structural hazard, which is very simple to understand. It just means if we don't have a functional unit to work with, we cannot deploy. So it will stall. And we have data hazards. Data hazards say that if all operands are available, only then we can do the execution. And that means we cannot do things like read after write and other data hazards that may harm us. So we have to stall these operations as well. And maybe other operations will be executed in this time. Instruction can be executed before its previous instructions. We don't care. As long as we have all the information that we need, we can execute it, and it will just wait in the reorder buffer. Ready instructions can be executed before the others. Out of order made our programs much, much faster. It utilizes the throughput of our CPUs in a very, very good way. Another thing that is very important to understand, all CPUs have caches. Caches made our life much easier as well, because accessing a memory, as long as the memory gets bigger and farther away from the CPU itself, it gets longer latency to get it. So you want your hot data to be in the fastest cache possible. And this works great with locality. If you are working with vector and you are using a cache-friendly algorithmic, it usually will be much faster than using an O1 data structure like an unordered map. Because everything is ordered, everything will be in the cache line, and you will just access it much, much faster. So it's very important to understand it. I just wanted to give it as a taste. Let's continue. What does it mean for us as a C++ developers? It means the standard says that data dependencies must be honored, which is okay. We must honor things. We must honor all dependencies. But it also says that the compiler may reorder any memory access under the SIF rule. That means that we can change anything that we want if we are keeping the SIF rule. And we will get to the SIF rule really soon. Different processors have different promises. When you work in your company on your code base, usually it's really important to understand what is your system running on. Because you may write code that is optimized for x86, but it will not be optimized on ARM, or maybe it will be just harmful in ARM. What is the What is the SIF rule? SIF rule means basically that we can change everything. We can change everything. We can change everything if the outcome of the program will stay the same as if it runs in a sequential consistency model. And from the SIF rule, we have a couple of smaller rules that explains exactly what it means. The first one says that volatile operations in the same thread must be committed in the order that the user wrote them. So volatiles in the same thread are usable. At program termination, if something was written into a file, it will be as if the program was running in a sequential mode. Prompting a text to a user to get inputs and will be prompt before, it must be prompt before the actual waiting to get those inputs. So we cannot reorder those things. And executing functions from external libraries. The compiler cannot see what's going on in your external library. So it assumes that all operations from the external libraries have consequences, or basically side effects. Because they have side effects, we cannot reorder them, because we don't know what will happen then. But good thing is, standard library is reordered. Is it a good thing? I don't know. As always in C++, there are rules that break the rules. So the most important rule is don't write undefined behavior. If you have undefined behavior in your code, SIF rule is not promised. That means everything can break. The compiler can do whatever it wants. It can change whatever it wants, even if you have a slightest thing there. And then you have the rules that break it for our benefit. The rule is copy elision. Since C++17, copy elisions are mandatory in the language. And that means that the compiler can remove constructors, destructors. Things are done differently. Maybe they are moved even. And everything is fine. It's just doing it for us, for our benefit, to get a faster code. And it actually works pretty nice. If you will see the same code, one moment, Chris. If you will see the same code, and you will compile it with C++17 and compile it with C++11, and you have RVO optimizations in your code, you will see that your performance in C++17 compilation standard is better. Yes, Chris?
All I was going to say on that one is just like to make sure that people don't think that like the compiler is just like removing copy constructors from their program. Like my understanding for that one for mandatory copy elision, like the wording around temporaries changed such that like formally speaking, those temporaries never existed in the first place. Like I just thought it was like it doesn't just randomly remove copies of temporaries, obviously.
Oh, of course it doesn't. Yeah. Again, because it does it for our benefit, it does it in a way that doesn't break your program, of course. Unlike undefined behavior that breaks your program. How does all of this affect multi-threading reordering? So let's start with a very, very simple example. We have two threads here. Each thread is trying to set a flag to 1. Thread 1 is trying to set flag 1 to 1. Thread 2 is trying to set flag 2 to 1. Then it checks if the flag is open, and only then it gets into a critical section. Basically, it's like mutex for poor people. What may happen here? Exactly, everything. But everything here is only two things, so it's a good thing. It may reorder the stores and the loads. So basically, it can move the storing of one after the checking in each of the threads, and then both threads will enter the critical section at the same time, and then we did nothing here, no mutual exclusion. On the other hand, we can create starvation. Each thread may wake up. Let's say the thread 1 woke up, set flag 1 to 1, then fall asleep because there's scheduling. Then thread 2 waking up, setting flag 2 to 1 as well. Then both threads wake up and they cannot enter critical section, and they will never be free, and we have deadlock. The remedy for that is sequential consistency. Sequential consistency means that over all threads and over all cores, your program will run as if it runs in a sequential order.
Overall course.
Over all cores. But it's very, very expensive, and we don't have it. Compilers do not provide it without price. If you want sequential consistency, you have to request sequential consistency. Not all operations provide it just like that. So if you will just write integers, they will not work that way. But what do we have? In C++, we have something that's called scdrf. scdrf is basically something that says, if you don't have data races in your program, it will run as if it's sequentially consistent. To achieve that, you need to give tools to the programmers. And those tools are synchronization tools. Basically, we must provide those tools so that we will have a tool to say how we synchronize and how we signal between threads that you shouldn't do something or you should wait for something. And that's exactly what most processors do. Here's an example of how it works. So think of S as some kind of synchronization mechanism. Let's say it's very, very familiar to the CUDA sync threads. It means all threads must get to this point, and only then they can return. And that means that we will get to the bar function on the flag in both threads exactly after both threads has gotten to the S, and only after that they can enter, and that means the thread 1 already done some work on flag. Small pop quiz. We have 4 threads. Thread 1 is setting x to 1, thread 2 is setting x to 2, thread 3 is setting y1 and y2 to x, and thread 4 is setting y3 and y4 to x. Can we get this? y1 equals 1, y2 equals 2, y3 equals 2, y4 equals 1. Who thinks yes? Who thinks no? And many people don't think anything. Okay. Okay.
Those are integers.
Those regular integers, nothing special about them. So people that thought that it is possible, you were right. And I will show you how it may happen in the timeline of the threads. So let's say that thread 1 is waking up and setting x to be 1. Then thread 3 is waking up and setting y1 to x, which means 1. Then thread 4, which reordered the operations, because it can, sets y4 to 1. Then thread 2 is woken up and sets x2 to 2. Then thread 3 is woken up and setting it to y2 to 2, and then thread 4 is waking up and setting y3 to 2. Might happen. Okay. Now, after we understand that we need synchronization tools, we need to understand how synchronization tools work and what do we have to work with. And I would love to start with the elephant in the room. Volatiles are not synchronization tools. Don't use them. If you are using multi-threaded, they will not promise anything in different threads. They will just promise something in the same thread. And that comes from the SIF rule. That means if you don't want some operation in the same thread to be relocated, or you don't want something to be cached, that's fine. Volatile still works like that, but it doesn't work with different threads. Let's look at a very simple example again. We have two threads here. We have volatile with integer. Volatile integer pointer that takes the address of y, which is a global, and it's provided to the two threads. Each thread runs from 0 to 50. One thread is trying to increment x by dereferencing, and one thread is trying to read from x. Basically, it should be fine because we used volatile in the correct way, but we created turn reads and turn writes here. On x86, it might work because most of the integer operations can be done in an atomic way, but still it's a problem on other systems, and you must understand that something like that will just break you. It will not keep you in sequential consistency, and you will have a data race here. Most of volatile functionality was deprecated in C++20. So it means that you won't be able to use it in C++26, I think. We don't understand how many things that were used with volatiles, they have no meaning. So, for example, what does int volatile parameter to a function means? I don't know. What's a return type of an integer that is a volatile? What does it mean? Compare exchange, it may fail. What does it mean for a volatile to fail? How will it act? We don't know. Is incremental operations are atomic? It's not defined. And if you want to know more about this, there is a great talk given by JF, which is the one that wrote the paper that volatile must be deprecated. And he goes deep into the rabbit hole and explains all those use cases that shouldn't be used. So you can go and watch it after this talk. Now let's talk about real synchronization tools. The synchronization tools have barriers, atomic operations, many different things. And the first of them is a basic barrier that is an assembler block. That means we can create a barrier that means operation cannot move through it. They cannot suppress it or surpass it. I said something. Okay. Here's an example of how we can do something like that. We have the thread 1 with a very long calculation that is very expensive. And then we have a memory fence. We are saying that we want something that is an assembler block that is requesting a memory fence and says that we want to use it on memory. That means that read-write operations will not be reordered over this fence. The same thing is done in thread 2, but it's waiting for the done. And that means that the done will be set to true if and only if very long calculation is actually done. Volatile is used, by the way, with this assembler block just to signal the compiler, please don't remove this. Because volatile operations have side effects. And if the compiler can see this and it will be without volatile, it might just remove it because it's not used anymore. Yes, Christine, you have a question?
I mean, how is just intuitively know not to remove something that's a
Assembler block,
like that's written as an assembler block?
but not all assembler operation have side effects, so it may remove them. And here you're signaling to the compiler, please don't. Please leave this fence. Yes?
Why do we need to omit an mfence instruction at all?
That's a great question. We don't. We have a lot of force because we are C and C++ developers. We have all these neat tools. We can write assembler. Don't. If you will write this code, and this is actual code that will work, and it will be in your code base, Peter will come and yell at you. Most of people don't understand what it does. It's really complicated, and we have all this force. We shouldn't use it all the time. We should use only the things that we need, and we will get there because the standard provides us with so many wonderful tools to do this job that we don't need to do it with assembler blocks. And as I said, most log and atomic operations are memory barriers. Now let's dive deep into the rabbit hole of the synchronization. What does it mean? What does memory order means? What does memory barrier means? And what are the types? Let's start with acquire semantics. So acquire semantics can be done on read operation. We don't care if it's read, modify, write operation or just a single load operation. We can ask the compiler, please do it as an acquire. And what does it mean when you write read acquire operation? It means that you are setting a fence after this operation, and all memory requests, reads, writes, no matter what, they cannot go upper. They can be reordered after the fence, but everything that is succeeding this operation that was read acquire cannot move up. It cannot be reordered. Then we have the release semantics. Release semantics is the opposite of the acquire semantics. It works on write operations, and it says that if we have a write operation, a store, or a read, modify, write operation, we can still do it with release semantics. It means almost the same thing, but the barrier is different. Now it means that we are putting a barrier, and all the operations that were before this operation cannot be reordered after this operation. And this is called half fence. It's not a full fence, it's a half fence.
Is it all memory operations or just like the write operations? Is it
all memory operations. They cannot move up in a read acquire, they cannot move down. In read acquire, they cannot move up. In a write release, they cannot go down. And then we have the full fence. Full fence is just using two fences together. We can say one operation will be read acquire, and the second operation will be write release, and everything between those operations cannot be reordered upper or down, those two barriers. But everything inside those barriers can be still reordered. Sequential consistency, we have that. We actually have that, and you can request the compiler to do it for you and the processor to do it for you, but it has a huge overhead. You have to understand to do something with sequential consistency means that it has to be seen exactly as it happens across all threads and all cores. That has a price to it. And that it looks almost exactly the same as read acquire and write release. But when you use sequential consistency between two operations here, all the instruction between those have to happen in the same order. They cannot be reordered even between the fences. They must happen in the same order, in all threads and all cores. You might ask yourself, what is the difference between read-release and read-acquire and write-release operation and sequential consistency? And it's a great way to do it with a simple example. We have a store-release operation and load-acquire operation. We have our 4 friends, the threads. 2 threads are trying to store into X and Y. And thread number 3 is trying to read from X and then read from Y with acquire. Then thread 4 is trying to read from Y and trying to read from X into Y4. Because it's read acquire and write release, the result might be like this. Y1 will be 1, Y2 will be 0, Y3 will be 2, Y4 will be 0. And that happens because read, acquire, and write release doesn't promise anything between cores. Let's say that thread 4 was in a different core. If we will use that, we can get those results. Most compilers will strengthen up and do it in a sequential consistency, but you cannot count on that. And the difference, And the difference is, if we will just change the load operations and the store operations to sequential consistency, then we are enforcing everything to be seen across all threads and across all cores exactly in sequential ordering. And so we will get exactly what we wanted. Yes?
So just to make sure I understand that, what we were saying on the previous one, so the compiler, when it sees these load acquires, will not order the the loads, but because the memory model may have different cores seeing different things, that's where we get this challenge.
Moreover, even it happens because you don't have relations between X and Y. If you had a relation between X and Y, read acquire and write release would even work with different threads, but you don't have relations between them. They're just 2 stores. We already know that we have sequential consistency, and we know that it's the most heavy operation to do across all threads and all CPUs and all cores. But then we have relaxed operations. Relaxed operations means it's free for all. We allow you to reorder everything. Everything is possible. Operation can go up the fence. Operation can go down the fence. The only thing it promises is that this operation that you want us to operate with relaxed semantics, it will be atomic. Just one instruction. That's it. That's all it promises. Maybe sometime you can use it for your advantage because almost no overhead. But usually, that's not what we want. And then we have something that I've been asked about many, many times, consume semantics. Who heard about consume semantics? Very few people.
I don't know what it means, I've heard of it.
That's all you know.
It consumes, exactly, no. Well, it's the most ambiguous one because it's not used. And it will, yeah?
It's just like unimplementable on most architectures. I think like
It has no effect.
That's what
It has no difference from acquire on
on
this.
most architectures. Like I think Alpha.
Alpha is the only one.
Alpha was like some sort of just like used.
Yeah, they tried and you could use it, but not even in Alpha. I think even in some ARM v7, you could use consume.
I think on ARM it's always just becomes acquired.
I need to check that because I think I compiled it with ARM v7, 32 bits, and it was, if I wrote it exactly as it wants it to be in consume, we will get to there, it actually was with consume. And actually my performance was better with consume. So what is it? Yes, great question. No one knows. Let's continue. Basically what it means is it's almost the same as release and acquire operations and semantics, but it's a little bit lighter, and some CPUs may take advantage of it. The only thing that is different, that it uses data chains. What does it mean in data chain? If you have a CPU that has to emit fences like ARMv7 or RISC, your code will look something like that. And the chaining of data means that, let's look at W8. So the first operation loads from memory into W8. The second operation adds W8, so it has relations. That means LDR must happen before add happens, right? We have dependencies, data dependencies between them. And then the store operation has data dependencies as well, because it uses the same W8 that we calculated in the previous one, and we store it into a memory. We created data dependency in this code. Inside this code, consume can be used. Data dependencies can be chained. That means that even if you have a couple of operations, we can pass them as a chain of dependencies. And you can see it between the two operations. The two loads are then used inside the add, and we must wait for those two. So the add operation will not work without W0 and W2. The second add will not work without W0 again. So we have a chain here as well, and the store operation is waiting for W0 there. What does it mean? The three last operations cannot be reordered because they have data hazards, but the two loads can be because they have no relations. The compiler sees those data dependencies, and then it can exploit it with the dependency chains. What the dependency chains mean, we have to carry a dependency. Carry a dependency is something that is defined in the C++ standard in many, many words that no one understands. But basically what it means is if you have an instruction and you have an operand, and this operand must be calculated in an instruction before this operand is executed, then it has a dependency on the previous instruction. And that's how it works. You have to have those dependencies if the compiler will see the dependencies, and you have the CPU that can actually use consume, you will get better performance. Now let's try to execute it. After you understand that we have to have a dependency on, and we have to have data chaining, let's try to write something that uses consume. So we have an atomic bool value that is set to be false, and we have just an integer that is x. That's it. Thread 1 is setting x to 1, and then storing true to a. Then in thread 2, we are trying to load consume from A to Z. We are checking if Z is not something that is false and it was actually changed. And let's assume that we have a loop that always tries to take it. And then it sets y to be x. Will this work? No. Who thinks it will work? No one? Yeah, it's an epic fail. It's a fail because you don't have carry a dependency between x and a. No dependencies at all. So you cannot use consume here. If it was acquire and release, yes, you could use it. But because you are trying to do something smart and use consume, it will not work. What can we do? So we have to change one thing. Instead of a being an atomic boolean, it has to be an atomic pointer to an integer that starts with null. Then thread 1 does almost the same thing, but instead of storing true, it stores the reference or the pointer to x. In thread 2, we are trying to load it with consume exactly the same way. But the difference is that y is set by dereferencing z. And we created a dependency. Because we are using the same z and it has a dependency on x, we have a consume dependency. And this will actually work. Yes?
Would this example work if thread 2 did the load relaxed?
No. Because relaxed doesn't do anything. It just says that this operation will be atomic, and that's it. You don't have a memory ordering between those operations. If you would say it is one of those operations is a write release and the other operation is a consume acquire, then you have ordering. But when you use relaxed, it may reorder it. It may go up, down, wherever it goes. It may go after the...
Well, sure, but if a pointer returned is not null, then what does reordering matter?
Well, the thing is that, then, like, potentially A moved down thread 1, out of thread 1's L1 cache into memory, but the cell, the X value, is still in the L1 cache of thread 1 and did not move all the way down. Okay, so the consume basically tells the CPU, hey, don't, like, you need to make sure that everything comes, like, through memory just the same way as it is. But if it was just a relaxed load, then it was okay for thread 2 to read just the address without making sure that everything else was flushed from fetch.
Correct. You don't have ordering between the threads, between the cores, between anything. So I just want to continue, and we may talk about it later. Yes?
So why pointer to x and not plain x as the argument being stored?
Because you need to create a dependency. If you will just take x, it's not really a dependency. You need to dereference it. And
Is there no dependency on the value of x?
no, but there is. But then you need to pay the price of copying. It goes between cores. Let's say you have a NUMA system here, and then you need to move it across the NUMA cores. It's pricier than just look at the memory. Sometimes.
This is a typical use case for consume when you want to like publish a pointer or something.
Mm-hmm. Anyone else? Yes.
I was just gonna say, so like, would it be fair to say that a consume fence then is just, like, it's less of a global fence essentially? Like, it only prevents reordering for things that are direct, that have direct data dependencies on whatever you're doing the actual load consume on. Okay.
Yes, exactly. It's exactly what it does. It promises only if you have data dependencies inside that thread between those operations, only then you will have the lock.
So in that case, then, like, store, release, and load acquire, like, the fact that you can call them on it, like, it's a member function of an actual atomic, always made me think that it was maybe smaller in scope. Like, those are always global fences in, like, the C++ memory model.
They have to be.
Okay.
That's the definition. When you use write release and read acquire, you are defining fences between threads. You are defining the ordering inside the memory between those threads. When you're using consume, you're not defining a fence here. Let's call it that. It's not a fence. It's just taking advantage. You are telling the compiler, hey, it's okay, I know there will be a dependency here. Don't put any fence there. It will be fine. Not always. Okay. I will not finish my slides. Okay. Good news, you don't need to use release acquire. You don't need to use consume because read release and write release and read acquire are more powerful, and most compilers will just use them. So it's a nice thing to know that you have consume and you can use it, but it's not usable. So Peter, you may relax. Now you know what consume is.
Finally.
This is an interesting, yes?
Quick question, how do you know if a compiler supports it or not? Do you need to read the assembly?
You need to understand, not the compiler, you need to understand the CPU you're working on. So if the CPU gives you the ability to use consume, and the CPU's compiler backend knows about consume and will actually use it, then you can use those things.
So how do you check that?
ISA, CPU has ISA published, so you look at the ISA, and then you understand if you have those fences, and they will write about memory ordering, and they will say, yes, we give you the consume, and then you can use consume. And if they give the consume, that means the backend for that CPU must provide it, usually.
And then how do I do the compiler for support?
Depends on the depends on the compiler. Depends on the compiler.
So there's no easy way to check.
Use Clang. It's easier to read the code. Okay. This is an interesting edge case for the release acquire and for memory ordering, sorry. So we have store release here, write release operation on A, and we have a load acquire operation on Y. Both of those operations have fences, right? What might happen here? Can it be reordered?
What is A1?
A1 is just an atomic value. Atomic something, atomic int.
It's a slot.
It's a good question. It's an atomic integer.
Can they be reordered? They can be reordered, right? What's preventing it from being reordered?
Exactly. Nothing. Why does it happen? So we have store release, and this is the fence that we have created. We have load acquire, and this is the fence that we have created. So in release, all operations that precede it cannot be moved after this fence. And in acquire, all operations that are successing our operation cannot be moved up over the fence. But nothing is said between those two. So basically, we can switch them. Now think about the things, if you write your code incorrectly with release acquire operations, what this can do. Potentially, if you write it incorrectly like that, you may create deadlocks. Okay, I will try to rush over this section, but we finished the memory ordering. Any more questions about memory ordering? No, great. And now this is the section that we talk about the tools that we have in C++ that we can work with. The most basic tool that we can use is thread. Who used pthreads? Pure pthreads. You're too happy about it.
The world you had it with.
All the old people use them, yes. Yeah. No, you just, you were really excited.
Got the job done.
Yeah, so it's not that bad to create a pthread, but it's much easier to create a thread. And moreover, stu threads are X-platform. That means you can create it in any operation. You're using Windows, it will create the Windows thread. You're using a Linux operation system, it will create the pthreads for you under the hood. So it's easier to use it. Thread local. Thread local is a nice thing that basically says that each thread has its own copy of a global variable. And that's great if you have threads that need to do something with a global variable, but you don't care about the state between them. You don't have to share the state. So here in this example, we are using that. We have a do count that count from 0 to count itself, and it incrementing ink. Then it returning the ink. Because we are using threads, and this will get better with the slides, we cannot return a value. So we need to use the reference. And here we are actually using the reference. We are saying, okay, I want RA to be as a reference into a thread, and I want to get it back because I want to use it. And in this case, thread 1 will count to 10, thread 2 will count to 20, then we'll join them and print them, and no surprises here. We got exactly what we wanted. An important thing to remember is that main is a thread as well. So it has its own value to print. C++ developers love to break things. And this is something that I actually saw in a code base. They used thread local, and they provided a memory address for that thread local. And if you are providing a memory address for that thread local from the main thread, it will provide you with the address from the main thread, and it's not local anymore. So if we will use it like that, we broke everything. And please, it's not fine. If something says thread local, use it for what it was invented. Don't abuse things, guys. Okay, finally, atomic operations. All the things we talk about with the memory fencing and how they work, how the release acquire things work, how all the semantics work, they are all used with stud atomics. You have all the operation you can think of when you're using stud atomic. We have all the memory orders, and by the way, I hide consume here for a reason, because you shouldn't use it. How do we use those things? We have two ways to use atomic operations. So we have fence operations. We can just ask the compiler, please create a fence here. And we can say what type of fence we want. So in thread 1, we want release order. And in thread 2, we want acquire order. That just means that A equals 42 cannot move under the fence. And in thread 2, the operation that sets R2 cannot move above the thread, above the fence. And that means we will have memory ordering. Still, you have to understand that those are atomic operations. They are not locking. That's why we have the C-select operation there.
So just so I also understand, it does mean that in thread 2, the value could be 0
or 42.
No matter, it just depends on the order that things were executed.
Yeah, in the order the threads were scheduled. No, the threads were scheduled, but the ordering should be the same. We can do the same thing with the actual operations. We can ask the store operation to be in release order, and we can ask the load operation to be in acquire order. It will just give us the fence, no reason to write those fence by hand, and we will get the same results. The default for the standard is that all atomic operations, if you don't specify what you want, they will be in sequential consistency. And that means the ordering of all the threads must remain the same, of all operation and all the threads. Performance, a bit about performance. So on x86, loads are just loads. We are not locking. On others, ARM, they will be locked. For stores, x86 uses exchange operations, full barriers. So you have to understand when you're using a store, you will pay for it. This is a nice example how to use atomic values. So we have a spin lock operation here. We have a spin bool foo that receives an atomic boolean flag. It will use exchange operation. Exchange operation means that it will always return the older value from the function, and we are trying to set it to true. If we already got true, that means that someone is still holding the lock. But if we got false, that means that we took the lock, we got false, we can exit the while function, while loop, we can print, then we can do other stuff, then we can print more and release the lock. In the main thread, we are creating the flag, we are creating the thread, the holder thread that takes the flag, sleeps for 1 second, prints that it's releasing the flag, sets it to false. Then another thread is actually using the spin lock. We are passing a stud reference to the flag, and then we are joining both threads, and we got exactly what we wanted. We got full synchronization between all threads. In C++20, we got stud share pointer as an atomic. As you know, a shared pointer is not thread safe. The only thing is thread safe there is the control block. Basically, you have an atomic variable there. And since C++20, we can say we want to use an atomic shared pointer. But the bummer is that it will always lock. In CppCon 2022, Timur talks about how to create a lockless atomic shared pointer. A great talk, you should listen to it. And this year, in 2023, Daniel Anderson showed us how to do it even better. So, very good talks, you should listen to them. Atomic buildings. The compiler provides us with all the atomic operations that C++ requires as a building operation. Basically, in Clang and GCC, we have the atomic reference. And that means, basically, buildings will take the best approach to create the atomics. The compilation will just change your atomic call to something that is assembler, the intrinsic operation. Question? Okay. I just wanted to state again how volatiles and atomic works. So we have a simple function. We have a global that's called sync. We have a function that it uses volatile. It takes a pointer to a volatile from sync, and then it just dereferences and returns it. The other function, it uses atomic. I just wanted to show you how to use the built-in operations. So I'm taking the built-in operation for the atomic, load n. I'm loading it, the sync, and I'm asking it to be a relaxed operation. Because I don't care, I just want it to be an atomic operation. If we will look at the x86 64-bit disassembly, they are the same. Yay. If you would look at the 32 bits x86, they are not the same operations. If you would look at the volatile version, you can already see in lines 7 and 8, it broken the load into two loads of the 32-bit world. That's not atomic in any way. And if we will look at the atomic operation, you can see that it does something smart here. Instead of using a fence, it's using a vectorized operation. It's using a vectorized operation to load a Q word. Pretty cute, right? x86 does interesting stuff. But CISC operations and the assembler might get too complicated. So I wanted to show you RISC-V, which is one of the simplest ISAs that I saw. And you can see it clearly. Even on RISC-V, 64-bit, volatile operation is not an atomic operation. It broken it down into two different operations. It calculates the address, and then it uses it with offset 0 to load it. But when you use it with an atomic, it does it in one place on the memory itself. Let's look at the 32-bit version. In the 32-bit version, you can see that it does almost the same thing as in the x86. It breaks it down into two load operations. But with an atomic operation, you can clearly see we're using a fence. Not as fast as x86, but good enough. This is one of the examples I want you to take away from this talk. And it's yes?
Maybe we should rephrase that and not say like not as fast as x86 just is always kind of doing fences for you. So it's kind of, x86 is kind of always slow, and this one at least has the opportunity to be a bit faster for all.
Yes and no. I would say yes and no, because the load operations on x86 are much faster than if you're putting a fence.
But that's because like writes are always...
And that's because CISC is a complicated beast. Okay, so I wanted to show you how to use fences correctly. We have a shared value here that is not atomic. And we have an atomic flag that is just an integer. We have a function that doesn't use acquire. It uses just relaxed operations here. It runs for a very long number. It tries to do compare exchange strong. The difference between compare exchange strong and compare exchange weak is faster, but it can fail, and then you need to loop around it. But here, I don't care about it. I say, I want it to be an actual operation that returns the correct value. The compare exchange will take the expected. It will compare what is in the flag right now with expected, which is 0. If it's actually what was expected, it will set it to 1 in one atomic operation. Then we have a shared value that we are incrementing, a count that we are incrementing, and then we are storing to flag, we are releasing. We are storing 0 back to flag, but in relaxed order as well. And if we will look at the x86 assembly, it's nice. It didn't reorder anything. But we can see that we have the compare exchange operation, which is good. We have the increment for shared value. But notice those lines. Those lines are important. We're incrementing RDX, and then we're storing it to the memory address. But it's not reordered here. And then we're storing 0 to flag atomically as well. Surprise. It fails. Even though the assembler was not reordered, the CPU reordered it for you. A shared value store and the flag store can be reordered there because of those. It broke down the storage into 2 operations. It incremented it in a register, and then it stored it. That was its only problem. If I would look almost at the same program that does almost the same thing, but we are just asking it to use a different memory ordering, an acquire memory order that puts a fence, and a release memory order that puts a fence, we can see that this assembly is almost the same, but it's not taking the register anymore. It removes the increment in the register, and it uses it directly on the memory. So it's a little bit slower, but still, this is an actual atomic operation. And of course, the program runs. And as I always stated, CISC is a beast that's hard to understand. Let's look at RISC-V. RISC-V, it's even easier to understand what's going on here. Yeah, maybe it's longer, but it's easier. In line 9, we're asking to load from A0. We're asked to load. You don't have a fence here. It's just a regular load. But then in line 16, it asks to do an AMO swap, which is compare exchange for the flag itself, because A5 is flag now. So one operation is not atomic, the other operation is kind of atomic, and it's not atomic. You can reorder everything here. But if we will look at the second function that use acquire, you can see clearly that the load is acquire load. We have a fence here. And then the store is not just a store for write release, it's a full fence. We are using a full fence here, and that's why this operation is actually atomic, and it actually will work. Other STL concurrencies, future and promise, I think everyone knows how they're used. They're used to communicate between 2 threads, so I don't need to provide references and account for the references. I can just push a promise, wait on a future, and get what I need. JThreads. JThreads are very, very good thing that was added in C++20. How many people here forgot to join their threads sometime? Exactly. You will not forget it anymore because you don't need it anymore. It will do it for you. So it's a very strong tool. You also got stop source with it. Stop source is a great way to stop your threads. It's a synchronization. You can request to stop a thread, And it may work on regular threads as well. You don't have to use it with JThreads, but JThreads has an internal stop source. This is a long example. You can read it afterwards. Mutexes and log guards, just things that you need to understand that are there. We have mutexes that are in standard, conditional variables. Log guards are just great tools to use RAII on mutexes. It will take the mutex in. When it gets out of scope, it will just release it for us. We have unique logs that are almost exactly the same as the log guards, but they can be dereferenced. They can be used in a log function that locks all of them together. Conditional variables work with unique logs. We have scoped logs. Scoped logs are always working with multiple logs. They will try to take all the logs together, and they are working with dead log avoidance algorithms. Great features that were added in C++20 are counting semaphores and binary semaphores. Counting semaphores is basically, finally, we have a semaphore in C++ that's already implemented for us. Counting semaphore can count to any number of threads that we want to arbitrarily use. Binary semaphore can count to 1. And this is a usage example. We have 3 semaphores. Each one of those semaphores are set to 0. We have a person speak function that receives a text that we want to display. A binary semaphore W, which will be the acquire semaphore. Binary semaphore R for release semaphore. At the start, we are trying to acquire. That means if the semaphore is 0, we cannot proceed. We will have to wait that someone will release us. Then we can print text. Then we sleep, and then we release another semaphore that we received. In the main thread, we are creating 2 J threads with person speak. First thread is saying hello, person 2. We are providing it with a start speak semaphore and person one spoken, sorry. Then we're providing P2 with hello, person 1. We're providing it with person 1 spoken and person 2 spoken. And then the main thread releases thread number 1, person 1. Person 1 can say hello to person 2. Then person 2 releases person 2. Person 1 releases person 2, and then it can speak. Then person 2 releases main thread, and it can say goodbye. And that's exactly what we got. This is an example with stop source. Let's say that we want a scheduler and we want the 2 people to speak to each other many times. So all we have to do here is to add stop talking to the same person speak function. And we are using a while operation here that we are saying that if the stop token, if we receive the stop request, we will stop this thread. We will join it. Otherwise, it's almost the same function as before. Then we have to create a scheduler function. The scheduler function just runs on all the stop sources. We have 2 stop sources here, and it will request the stop for each one of those. In main, we are creating the stop sources. We are creating the threads. We are providing them with the stop source. We are doing the start speaking. We are releasing it. We are starting the scheduler. Then we are releasing P done. And if person 2 done speaking, we can say goodbye. And that's exactly what we are getting. We fully synchronize the 2 threads. We fully synchronize the 2 threads, and we got 4 times person 1, hello person 1, hello person 2, 4 times hello person 1, and a goodbye. As I mentioned, JThreads have their own stop sources. So you can provide your own stop source if, for example, if you want something to be localized and you want to use a special stop source in all threads. But if you don't want it and you want to use your own JThread stop source, all you have to do is change the location of the parameter to the first parameter to the thread function. And JThread will just push it for us. So it's almost the same, just we move the first operator, the stop token, to be the first parameter to the function. The stop speaking function is exactly the same. We are starting the 2 JThreads. after we started the 2 J threads, we can create the array of the stop sources to provide them to the scheduler, and then we will get the same functionality as before. I have created a small micro benchmark for all the playground that I used. You can find it in one of my posts in LinkedIn. You can play with the playground. You can see the benchmarking. So the good news is using threads, P threads, J threads are the same performance. The only problem I had, and it was me, I wrote bad code for the first attempt. And when I fixed it, everything just became noise. We have latches and barriers. Latches is something that means that all threads have to come through the same latch, and only then we get released. And barriers, the only difference between them is that latch is one-shot operation, and barriers can be repeated. So this is a latch example. A latch example, we have a vector of people that are going to do a work. We are creating a job latch in the size of people. That means we will have 4 threads working. We have a go home latch with 1 thread. And we have the job itself. The job itself getting the jobs, the go home latch, and the name of the person that's gonna do the job. We are printing the Mr. X that's gonna do the job. We are counting down the jobs, and then we are waiting on go home for someone to release for us. Then we are printing Mr. X is going home. Afterwards, we are creating the J threads and pushing the names to them. And then we are waiting on jobs. That means all threads have to count down. Only then the main thread will be released. It will print go home now. And then we are counting down the go home latch. And that means all the threads will be released, and they will print we are going home. So as you can see, we are starting a job, we are going home, and then all people are going home. This is almost the same example, but with a barrier. For barrier, we need to use a callback operation because we want to fire it twice. So in the callback operation, we just have a static variable x that is equal to 0. We are incrementing x with a post increment. That means that we will get the previous value from it. If it's 0, we will print go home. If it's 1, we will print done. Then we will need just 1 barrier for this job in the size of people that are working, and we are providing it with the on completion task. The job is almost the same, but it's clearer because you don't need 2 latches. You are just saying arrive and wait. Arrive and wait is really close to what's happening in CUDA when you say sync threads. It means all threads have to get here for us to release. And only when all threads will get there, an on completion will be called, and then they will fire it again because the count will start over. And when the count will start over, we will have other prints. So we will have the same thing as before. Shared mutexes, timed mutexes, things that you should know about. Shared mutex example, I will skip over that. Since C++11, it's an important thing. I think all of you know that, but since C++11, statics are magic, and they will log the variables for you. And if you will look at x86 disassembly, we can see that it's a guarded value. That means that only 1 thread will be able to do something with it. So we don't have the initiation fiasco anymore. Call once is just a way, if you have a function that you're running on many threads and you want it to be ran just once on 1 thread, the first thread that gets it, you can do it with once flag, and that's how you create it. You call stud call once, you provide it with a flag, and you provide it with what you want to do, and then both threads will just print 11, because just 1 thread could increase it. Package task is just a neat way to package something that you will want to work with asynchronously. It's not starting a thread for you. If you want it on a thread, you need to say that I want a package test on a thread, but it has its own feature. and you will get its return value or exception on the state that it stores inside it. And I don't believe it, but I finished all the slides. So, questions, anyone? Okay. Yes, Chris.
Is there, can you think of any use case where like std thread would be preferable to std jthread?
Wow, that's a good question. Because the performance is the same,
Yeah, that's my thought. It seems
if you have C++20, use JThread.
JThread detachable?
that's a good question. Actually, you would have to assume not, actually. Yeah.
Using thread, you can use something detachable.
Okay.
Oh, if you want, but you can, but it's better to use thread to detach things.
That, the use case.
Yeah.
Yeah, I mean, detached threads are always kind of iffy anyway, but there are legitimate reasons.
They are iffy. If you are detaching, something is wrong. Roy, you had a question?
JThread has a detach method on it.
Yeah, it has. Yeah. Yeah.
Are the atomics worth it? Like, it seems so complicated.
What do you mean? C++ is complicated. That's why we love it. We love masochism. We love to hurt ourselves. Yes.
You didn't cover async, standard async.
Standard async.
You covered Patrick fast, you covered everything.
You mean with coroutines?
No, just
Oh, you mean I didn't have time. It was one of the slides that I removed. Anyone else? Great then. Another question from Roy. Yes.
Maybe a word or two about the debugging problems related to these things, or
When you use multi-threaded operations, it's harder to debug, but you can use sanitizers, which help a lot. And please, guys, use sanitizers for your job. Actually, for me, I use undefined behavior sanitizer, and I use other sanitizer, and it helps me with 90% of my problems in multi-threading. All right, thank you.